In our previous videos, we were doing trend forecasting with linear and polynomials. Let's look now at logarithmic and exponential. So with linear, as time increases, your thing that you're trying to forecast either goes up or goes down, like we see here. With a polynomial, it can go up then down or down then up if you have a polynomial of degree 2, or if you have a polynomial of degree 3, then it has 3 terms, so it goes up then up, or down then up then down. Of course, you can have polynomials of higher degrees. All you're doing is adding more terms. What we want to look at in this video is logarithmic and exponential. So logarithmic assumes a steep increase initially and then starts to flatten out. Exponential assumes that there's not a lot of change initially and then it gets steeper and steeper. So logarithmic and exponential are related to each other. There are other types of trend forecasts, such as the growth curve, looks kind of like an S, that are beyond the scope of this operations management course, but will be discussed in business intelligence and analytics or in the statistical analyst micro-credential. So if you want to do forecasting that's logarithmic or exponential, you can work along with us. We are here on drpowers.github.io/mgmt-in-python. And we are working through this forecasting workbook. So click on this forecasting workbook, go into GitHub. It links you to Google Colab. And so open in Google Colab, and then once there, log into your Google account. This gives you a copy that you can then run and edit. So if you want to run it, you need to sign in. If you want to edit it, you need to copy it to your drive so it's yours to do with as you wish. So I'm just going to go into the one that I'm logged into. And if you have not been working through the previous videos, you will need to import pandas and import numpy so that you can manipulate the data. And then we are graphing, so I'm just going to scroll down to the section related to trend forecasting. And because we are graphing, you're going to need this matplotlib.pyplot as PLT, so make sure you import that as well. In our previous videos, we did a linear forecast, and so we took our data, before I get too far here, we imported data related to the number of complaints to our business, so make sure you import the C equals. This is the list of the number of complaints as well as the periods that go with them. So in period 1, there were 63 complaints, in period 2, 65, in period 3, 55. We then turn this into a data frame, a table, by using this pd.dataframe_list_zip. And we took the information as columns. So first the period, then the complaints, and we gave the columns names, a period, and complaints. So make sure you have created this CT, this complaints table, in order to do our forecasting. So in our previous videos, we fit a linear model. We found a formula for that linear model. We then plotted that linear model against the data and forecasted 3 points into the future. We also saw how well that model fit. We did the same thing with polynomials. So we used polyfit and plotted a polynomial of degree 2, used that to create a polynomial function. We saw how well that one fit. We plotted that information along with the three forecasted values into the future. And we also looked at a polynomial of degree 3. That's what you see here. And we looked at a polynomial of degree 4. That's what you're seeing here. So to look at 2 more types of trends, let's look at logarithmic and exponential. To do logarithmic, we're going to use numpy, so make sure you have that installed. And you can call your polynomial whatever you want. We just happen to call it AB here, just for simplicity. And so we are going to use polyfit. And the way that you do logarithmic, or the simplest way to do the logarithmic, is to take the polynomial command polyfit and just amend the data to be logarithmic. So what you see here is that we are applying a log to the time column. So from our complaint table, we have the column called period. We're going to find the log of those values, and we are then going to apply a polynomial of degree 1 versus the complaints. So when you do that and you type in AB, we get an array that says 10.19855.2315. We're going to turn this into a logarithmic function by taking that first value, the 10.19, that's the AB in the index 0 location, and we're going to multiply that times the log of the period of the time, and we're going to add the AB in the first index location, that's the 55.23. So what the hell does all that mean? What that means is that our logarithmic function is that our complaints, so we'll just type this in English, our complaints, our value y, is equal to 10.198, so we'll call it 10.2 log of whatever our x is. So here it's going to be the period 1, 2, 3, 4, 5, 6, 7, 8, and then you add to that 55. So the idea here is the complaints start at 55, and then it has that logarithmic shape for the rest of the data. So remember, a logarithmic shape goes up and then flattens out. So we're going to start here at 55 and we'll go up, and then that shape, that logarithmic shape, is going to be related to our 10.2 here, multiply times 10.2. So we'll see what that looks like in just a moment. Since we've already defined r squared in a previous video, make sure you run that. So remember, when you're using the polynomial functions, it doesn't automatically calculate r squared, so you have to use this definition here, compute r squared. Just run that just as it is, and that way you can call it later to see how well the model fits. So with our logarithmic, we call this compute r squared, we give it the complaints, and we give it the forecasted values that we just got here with our logarithmic formula. So when we do that, we find that this model doesn't fit very well. What this tells us is 41% of the variability in the period explains the number of complaints. And so a logarithmic shape is probably not the appropriate shape for this type of data. A logarithmic shape assumes the number of complaints increases quite quickly and then just flattens off. So we want to forecast into the future, forecast periods 9, 10, and 11. So we need to create that x2, convert it into an array. And then we're going to take that x2 and stick it into that formula for our predicted values. So we have AB, index periods, index 0, times the log of x2 plus AB, index 1. So notice this formula here looks the same as this one right here. The difference is, instead of using the complaint table periods, we want to use x2, which is those future periods 9, 10, and 11. That's the only difference there. The rest of this is the same. So we run that, and what we get is for period 9, it's predicting 77.6 complaints. For period 10, it's predicting 78.7 complaints. For period 11, it's predicting 79.686 complaints. So notice it's flattening off, right? That logarithmic shape, it increases, and then it starts to flatten. To plot this information, we plot the original data, so that's the complaint table periods versus the complaint table complaints. No lines, just dots. Then we plot the complaint table periods and the forecasted values. This gives us our logarithmic function. We're going to make that a thick line. And then we want to plot our future periods, that's the x2, versus the predicted complaints for those periods. We'll make it dots. We'll use a dashed line. If you want to add a grid, we can do that too. We add some labels for x and y. So what we see here is that logarithmic function, just as we predicted. It goes up steeply and then flattens out. You can see it does not fit the data very well. you can see that it's forecasting these three values for the future. So logarithmic function doesn't really represent our complaint data, but it might be that it fits the data that you are doing. In which case you can use the same code just as we did. The difference is the CT period is going to be your column of time, and then CT complaints is going to be your column of data you're trying to predict, and then the rest you can just crank out as is. You would change the 9, 10, 11 to be your future periods, whatever those might be. Those might be dates, 2022, 2023, 2024, or they might be time 15 times 16 times 17, however you're measuring your periods. The rest you can do just with the code that you have here. Let's try one more. Let's do the exponential. To do an exponential function, again, we're going to use the polynomial to make it quick and easy. So we are going to do a polyfit. And notice the difference here is that we're going to apply the log to the complaints. So there's a lot of similarity, right, between a logarithmic function and an exponential function. They're just kind of flipped over. And so because of that, we can get to them by just taking the log of not the x value, but here of the y value. So we'll do np.polyfit, then our complaint table, the column period, and then the log of the complaint table complaint, and we'll apply the polynomial of degree 1 here. We output what we're calling AB. That AB here we use in order to calculate the actual function. So to predict the values, we are going to find the exponential value of, and then what this is saying here, I'm just going to add in the text so we can say what this is. So our complaints, y, are equal to, so taking the exponential value of, and then what this is telling you here with the poly value here is that this is 0.05x plus, what do we got here, 3.99. So actually I'll just, let's move this down below this one, and let's get rid of this one. So our formula here, take the exponential of the polyval of AB and the periods. All that's doing is taking the exponential of 0.05, which is that AB 0 place, x plus 399. So you have a polynomial here in the exponential. So how well does that fit? Well, if we have run that definition compute r squared previously, we can simply call it with our new forecasted values. So we got to make sure we've run those. And what we see here is the exponential has an r squared of 0.66, which is better than the logarithmic, not as high as the polynomials we saw in the previous videos. We can then take future values, so future periods, period 9, 10, 11. We'll call that x2, turn that into an array, and then we want to put that into that same formula. So this np.exp, np.polyval, ab, comma, ct, period. We replace the part that's the complaint table period column with our new x2 values, but the rest of the calculation is the same. It's taking the exponential of, and then it's taking those values from the fit and putting it into an exponential function. So we run that. What that tells us is in period 9, it's predicting number of complaints be 85.63, in period 10, 90.14, and in period 11, 94.9. So you can see then, remember the exponential starts out flat and then gets steeper. So it's at increasing in the future. All right, let's see what the graph looks like. Let's plot the original data, the time period, and the complaints. We'll just make them dots, no line. Then we will add in a plot with the time period and our predicted values. That's going to be our exponential function. We'll make that a nice thick line. Then we're going to plot those future values of x. So that's 9, 10, 11. And the predicted complaints that go with them. We'll make those dots with a dashed line. And we can label the X and Y axes. We can add a grid if we want. And then we tell it to show the graph. So our exponential function here, we see that increase. We miss kind of the flat part at the beginning. And you can see it doesn't fit the data particularly well. It's possible, though, that you might have exponential growth. So if you think about things multiplying, populations, those are going to have more of this exponential growth. This might fit your data better. The complaints data isn't really an exponential growth type of data set.